Today we are going to discuss the traveling salesman problem. In traveling salesman problem, what happens? Basically, you have n cities. Suppose a traveler is there, a salesman is there. Salesman will start from his home, and after that the salesman will visit each and every city and ultimately come back to the his home only. So, this is the traveling salesman problem, and we want to find out the shortest route by which the time will be minimum. Let us see. By in general, given a list of cities and their pairwise distances, what we have to find? We have to find out the shortest route that visit each city exactly once. Please note this thing, that the each city is visited exactly once. We will see that it will enter one city only once and it will exit one city only once, not more than once, and also we will come back to the where we have started. Next, if you see, we are telling that it is a well known NP-hard combinatorial optimization problem. Now, what do you mean by NP-hard optimization problem or NP-hard problem? Basically, NP-hard means the problem which can be solved in non-deterministic polynomial time. Usually, if we can solve a problem in the polynomial time, it is fine, but there are problems just like traveling salesman problem which cannot be solved in non-deterministic the polynomial time. For this reason, we call it as the NP-hard problem. We will see afterwards that the traveling salesman problem is the NP complete problem, that is the problem can be solved in the polynomial time, then all the NP complete problems also can be solved in the polynomial time. So, this is NP-hard problem, that means we can obtain the approximate solution. Therefore, the role model of TSP, as I was telling you, obviously is a traveling salesman who come out from his home, start his selling from a particular city and visit each city once and return to his home at the end of the day again. So, basically if you see, there are n cities. If I draw something like this way, there are n cities which I am marking by these nodes. So, cities are C1, C2, C3, C4, C5, something like this. So, from his home he starts, he has to visit all the cities one after another. The path may be so many, that is I may visit C1, C2, C3, C4, C5 and then again I can come back to this. That is one path may be C1, C2, C3, C4, C5 and then again come back to C1. Similarly, I may go like this C1, then I can visit like this way also, that is C1, C5, then C4, C3, C2 and then again I can come back to the original one. So, if you see like these different combinations can be made. In general, if we say that if we have n cities, then there are total number of possible paths will be factorial n minus 1 from here. So, you can understand if the number of cities are more, then what would be the complexity of finding this all these paths, because from these paths we have to find out what is the optimum path, that is the path which will take the minimum time. As I was telling you, this is the basically the distance to cover from C1 to CT. It may be distance, it may be time, whatever it may be. So, in factorial n minus time, factorial n minus 1 possibilities are there to cover n cities. So, that I was telling that there are salesman has to visit n cities, then he has n factorial n minus 1 possible choices. Round the trip means from where the salesman is starting, he has to come back on the same city. Now, since the salesman has to visit all the n cities, the optimal solution obviously will be independent of the selection of the starting problem. That is, whatever starting problem it may be, you will come back to the original one. You can start from any city. Now, the TSP, if you see what are the practical application in manufacturing system, we can apply this traveling salesman problem in plane routing system, telephone routing system, in network, in traveling salesman problem as I was telling, genome sequencing, job sequencing, like this way various applications are there of this traveling salesman problem. So, in summarize, if you say, we can tell that The problem can be formulated basically from the two perspectives. One, I have to minimize the travelling time maybe, that is whenever you are travelling, the travelling time may be considered and I have to minimize the travelling time so that I can visit all the cities only once, or you can pose the problem as minimize the travelling distance. So, the problem can be represented as a network where the nodes and arcs represent the cities and the distance between them respectively. Or in other sense, I want to say that I drawn this one, I drawn it something like a graph, and from the graph I have to find out basically the shortest path so that each city has been visited exactly once and there is a cycle, means from where you have started you have to come back from this. So, basically I can solve it by graphically, I can represent the problem as a graph where I will have node, I will have arcs, and obviously I can find out some mechanism over there. So, what are the decision variables? There are certain decision variables are there, where if you see, we are telling there are n cities and we have to define basically a Boolean matrix X, which is interpreted as follows, as we have written small x I j equals 1 if city j is reachable from city I, that is if there is a connection between city I and city j, in that case x I j equals 1, otherwise if there is no connection we say that it is not reachable. Or in other sense, I will form a matrix like this way, where maybe there will be C 1, C 2, C n cities are there, like this way you will form the matrix. This I am from C 1 to C 1, C 2 to C 2, C n to C n, nothing will come. From C 1 to C 2, if there is space, that is if we can move, then if we can reach it will be 1, otherwise it will be 0. So, like this way some will be 1, some will be 0, and you can matrix 1, you can formulate one Boolean matrix from here. And suppose your d I j is the distance from the city I to city j. If d I j is the distance from city I to your city j. So, if d I j is the distance from city I to city j, we can formulate the problem as this: minimize z equals summation over I equals 1 to n, summation over I equals 1 to n, summation j equals 1 to n, d I j x I j, and your subject to summation j equals 1 to n, x I j equals 1, because they can take only one values. Here your I is 1 to n. Similarly, summation over I equals 1 to n x I j, this is equals 1. So, j equals 1 to n, and obviously, x I j, the decision variables, can take only two values, that is 0 or 1, which actually I have shown in the next slide. If you see the minimize this one, summation over I equals 1 to n, j equals 1 to n, x I j d I j, where your d I j is the distance from city 1 to city n. If you note, we have written d I j, this is equals to d I j, this is equals infinity whenever I is equals to j, that is the distance it is. We are assuming for the same I and j, that is on the same city, the distance will be remaining 1. So, if you see the problem, the next one is summation over j equals 1 to n, x I j equals 1, summation I equals 1 to n, x I j equals to 1. These conditions are coming due to the reason that your each city has to be exited only once, and each city must be entered exactly once. So, these are the two extra conditions. So, if you see the problem over here now, this problem if you remember these constants, if you see constant 1, constant 2 and this constant 3, and subject to your this minimization problem, this problem basically defines a regular assignment problem. If you see, this is nothing but the regular assignment problem, or in other sense I want to say that if we can formulate a traveling salesman problem like the problem minimize z equals summation over I equals 1 to n summation j equals 1 to n zij cij into d xij into dij subject to the constants 1, 2, 3, we can solve it using modified assignment problems. So, we can solve this problem using the modified assignment problem also, and other way what I told you just now, that is we can represent the problem as a graph, and from the graph we can find out the shortest path. So, that with a condition that it has to be exactly cyclic and each city has to be visited once, and we will come back to the city from where we have started. So, your special case is your the transportation traveling salesman problem can be applied if you see in machine scheduling operations also. Why I am coming to the machine scheduling operation? Because whenever you are talking about the machine scheduling operation, it can be posed as an assignment problem and you can solve it using the assignment algorithm whatever we have done earlier. So, first we will discuss that part, graphical also I will tell first, but before solution I will start with the assignment, then we will see the graphical. Let us see how we can represent. There are n items q1, q2, qn are to be processed on a machine in a scheduled time period. Okay. So, n items are there, we want to process on a machine. So, the problem for us is that we have to choose a sequence of these items, that is which item should be processed first on the machine, which item should be processed second, like this. So, we are assuming setup cost of the machine where item j is followed by item I is followed by item aj is cij. So, basically now we are telling what is the cost. In terms of cost, we are telling that the from item I ai to item aj the cost is cij. So, here you are using the cost and we are assuming that obviously that I told you little earlier that xij this is equals 1 if aij is followed ai is followed by aj, xij equals 0, otherwise that means if there is a connection between the items, which item is followed by which one, for that case xij will be 1, otherwise xij equals infinity. Additionally, cij will be infinity whenever I equals j, that is for x 1 1 1 2 2 3 3 like this, or for the diagonals of the matrix always it will be the cost will be taken as infinity. And the third point, if you see only one xij this is equals 1 for each value of I and each value of j. So, basically for one case only xij will be 1 and for other case it will be equals to 0. So, the machine scheduling problem can be used like this. So, in view of this, the assignment problem can be used to solve the above problem with an extra constant that we will see. The solution method, if you see, the solution method will be something like this. I have to solve the assignment problem. We know how to solve an assignment problem. If the given solution satisfy the additional constant of the transportation of the traveling salesman problem, then this solution is optimum. Optimum now additional constant means where I want to say from where I have started I should come back to the original starting position, or in other sense it should be cyclic. So, this is the additional condition. Now, if the solution of the AP does not satisfy the additional constant, then some enumeration method we will use. Obviously, we will explain this both cases with the examples. So, in the traveling salesman problem, the salesman obviously has to visit all the n cities. Now, as I told you, modeling of the traveling salesman problem as a complete graph with n vertices, the salesman has to basically make one Hamiltonian cycle by visiting each city exactly once and finishing at the city where he starts from. Or in other sense, as I was telling you, if you see this earlier figure, in this figure if you start from this C1, If you start from C1, you can visit in any way, but ultimately you have to come back to this C1 only. And we have to form with this, we are calling as the Hamiltonian cycle, and each city you are visiting only once and you are coming back to the earlier position. And of course, we are assuming that the cost associated with travelling from city I to city j is an integer, and the salesman wishes to make the tour whose total cost is minimum. Obviously, if the cost associated, you are assuming cost moving cost from C1 to C2, it may be 10, it may be 7, it may be 15, something like this way. So, the cost is there. Obvious, the problem is we have to minimize the cost. We have to minimize the cost. If you see, the total cost is minimum, where the total cost is the sum of individual edge costs, that is, or you can say it as the edge weight. You see this particular diagram, you have the 4 cities, we are telling K means KGP, A Asansol se, D Durgapur, and H is Haldia. On the figure, if you see, there are routes from K to A and the associated cost is 400. Similarly, from K to H, you can move, the associated cost is 300, like this. So, we can formulate one cost matrix immediately. The cost matrix can be calculated like this. You are having K, A, D and H, and here it is also row wise K, A, D, H. Now, from K to K, there is no associated cost. So, we are giving one blank space. If you see the figure again, from K to A, on the figure K to A, it is your 400. If you see, K to A is 400, your K to D, if you see, K to D is 100, K to H is 300. So, this you can write down now on this matrix. So, K to A is 400, K to D is 100 and K to H is 300. Similarly, we can fill up the other parts, just I am filling up. This one will be blank, this is 200, this is 100, and for D to K it is 100, 200, it is blank and it is 500. For H it is 300, it is 100, 500 and this one is blank. Suppose that the salesman wants to start from K. If you see, the salesman wants to start from K. Whenever they are starting, wants to start from K, and if you see the figure over there, just let us see the figure. We can move in any direction. I can say that I can move from K to H, then H to D, D to A to again K. Like this way, so many paths I can avail, and for each path I have to find out the associated cost. If you see, for K to H it is 300, H to D it is 500, that is 500 plus 300, 800, D to A is 200, that is 1000, and A to K is 400, that is 1400. So, if you write down K to H, then H to D, D to A and A to K. The associated cost from here you can find out. K to H is 300, H to D it is 500. From this cost matrix you can get D to A it is 100, D to A it is 200, and the last one is A to K it is 400. So, the cost is your 8, 10, 1400. But from here, if you see, if I make the path as like this, K to D, D to A to H, H to K. If I can make another path like this, K to D it is moving from D to K to D it is 100, D to A is 200, then A to H is 100 and H to K is 300. So, the total cost becomes 700 only. So, like this way I have to find out basically all possible paths, and then I have to check which path gives me the lowest cost, and that will be the optimum solution over here. So, like this way you are having so many paths, and from here you will find out what is the minimum path. So, whenever n is very large, it is very difficult to find out all the cases. So, the travelling salesman problem, if you see, can be described as a triplet set of 3 elements G, C and K, where G is the complete graph. I am talking now in terms of graph only, and your a cost function is there, which I am writing C such that V to V, and G has a travelling salesman tour whose cost is with cost less than equals T, with cost is less than equals T. And the travelling salesman problem, of course, as I told you, it is the NP complete problem, that is, it can be solved in the polynomial time. It can be solved in the polynomial time. So, we say that it is in NP complete problem. Now, in order to develop the solution procedure for the travelling salesman problem, one more condition has to be used, that if you see, we have written C of u v plus C of v w should be greater than equals C of u w. That is, if I am writing here C of u v plus C of v w, that is cost of this should be less than equals C of u w. Or in other sense, whenever I want to move from u to w, directly you can move from u to w, or for some other reason you can use some other path, that is from u 2 I will move to C T v, from C T v I will move to C T w. But in that case, the cost of both should be less than equals the or less than equals the original cost, that is, if you move directly, the cost always should be less than equals. It is this property, of course, we say that it is obvious, since mostly the direct journey, of course, is the cheaper than the the break journeys, it is well known to us. Now, the solution of the transportation problem, if you see what we have to do. First, I am going through the solution as the transportation problem, then I will see the next one, that is, as I told you, the not transportation problem, but the travelling salesman problem can be treated as assignment problem, or the travelling salesman problem can be treated as a graph also. So, first we will try to find out the solution as a of the travelling salesman problem as the assignment problem. So, what are the steps to be followed, that first we are telling, then we will discuss it with examples. First one, if you see, I have to reduce the cost matrix, that is known to us. For finding the solution of assignment problem, we use it, that is, first subtract the minimum elements row wise and column wise, that is, find out the row minimum, subtract it from each row, then find the column minimum, subtract it from each column. Then I have to draw a minimum number of lines which will cover all the zeros of that matrix. So, we have formulated the cost matrix. Now, if I draw the minimum number of lines to cover all zeros or not. Now, if number of lines is equals to order of the matrix, then the solution is optimal for the assignment problem. So, if it is not, in that case, I have to first find out what is the optimal solution of the assignment problem. So, you have to note one thing, you will treat the problem, you have the cost matrix, treat it as an assignment problem. Just we solve the assignment problem on the same way you solve the assignment problem. So, you are finding out the number of lines which will cover all the zeros. If it happens that the number of lines is less than equals the order of the matrix, since the matrix is a square matrix. So, if it is less than equals order of the matrix, then you know you have to find out the lowest element, and from the lowest element you have to subtract the uncovered lines, uncovered elements, and wherever there is a intersection you have to add, that part we have discussed earlier. So, first find out the optimal solution of the assignment problem. This is the first step. In the second step, once I have obtained the optimum solution of the assignment problem, now we have to find out or inspect whether it is the optimal solution of the travelling salesman problem or not. That is, travelling salesman problem is having another criteria. The criteria is it has to be cyclic, that is, from where you started you have to visit two problems. One is you have to visit each city only once, and from where you have started you should come back to the original position. So, that you have to check. Now, if the assignment schedule is such that it forms a closed loop or cycle, as I was telling you, and it consists of every city then stop, that is it has covered every city and it is forming a closed loop, then you stop, and this solution of the optimal problem is the solution of the traveling salesman problem also. Otherwise, you go to the next step. In the next step, what actually we have to do? We will try to find out the next best solution, which will be cyclic and this one. So, for this what I have to do? We have to find out the next minimum element of the matrix, that is you have the cost matrix. I have to find out the minimum element which is greater than 0, say it is k, and which we will include in the solution, that is that element k will be one optimum solution, and then find out if and then you find out the assignment of the other elements also. Now, if k occurs more than once, then for each case you have to repeat the process, which I will show you with one example. So, let us go to the example. You consider there are 5 cities and the cost between them is pairwise city pairs are given, just like C 1 C 1 it is blank, and C 1 C 2 14, C 3 C 1 C 3 10, like this way. So, at first I will rewrite the the traveling salesman problem as an assignment problem with the cost for C 1 to C 1 as infinity. As I told you, C I j is equals to infinity whenever I equals j. So, at first what you are getting? You are having the matrix over here, you are having C 1, C 2, C 3, C 4 and C 5. Similarly, here also you are having C 1, C 2, C 3, C 4 and C 5. I am just doing it initially. So, this C 1 to C 1 infinity, C 2 to C 2 infinity, C 3 to C 3 infinity, C 4 to C 4 infinity, C 5 to C 5 infinity, and all other elements whatever was there in the cost matrix, that is first row will be 14, 10, 24, 41, like this. So, it is 14, 10, 24, 41. The next one will come, just I am copying it, 6, 10, 12 and 10. The next one will be 7, 13, infinity, then 8, 15, 11, 14, 30, infinity and 17. The last one will be 6, 8, 12, 16, infinity. So, this is the assignment problem which we got by making C I j as infinity, as C 1 1, C 2 2, like this way. First thing is subtract the minimum row element from each row. For the first row, minimum row element is 10. So, what I am telling you, again I am not explaining that part properly, because already we have done this thing, C 1, C 2, C 3, C 4 and you are having C 5, C 1, C 2, C 3, C 4 and C 5. So, if your minimum is 10 over here, so that it becomes 4 0, 4 0, 14 and 31. So, this is infinity subtracting 10. So, 4 0, 14 and 31. In the next row, if you see, the minimum element is 6. So, subtract it. So, just like that way I am now writing, it will be 4, 6 and 4. For the next one, the minimum element is 7. So, it will be 0, 6, infinity, 1 and 8. For the next one, again it is 11 is the minimum element. So, it will become 0, 3, 19, infinity and 6. For the last one, 6 is the minimum element. So, 0, 2, 6, 8 and infinity. So, by subtracting each row you are getting it. Now, what I have to do? I have to subtract the minimum from each column. So, again you are having C 1, C 2, C 3, C 4 and C 5. On these you are having C 1, C 2, C 3, C 4 and C 5. In the first column already 0 is there. So, there will be no change. In the second column, if you see, the minimum element is 2. So, it will be subtracted. So, that you will get 2, infinity, you have 4, 1 and 0. In the next one already you are having 0. So, there will be no change, 0, 4, infinity, 19 and 6. in the next one minimum element is 1. So, it will be 13, 5, 0, infinity and 7. In the last row minimum element is 4. So, it will become 27, 0, 4, 2 and infinity. So, if you see here now the in this case what we are doing, you are finding the minimum of row and column. Now, try to make the number of rows, number of columns, number of lines you draw, so that you can delete all the rows and all the columns. So, one I can draw a line like this, one if I want I can do it, 2 I can do 3, 4, this is not covered. So, I can make 5. So, if you see now you are making the number of lines which are covering all the elements. So, it has covered all the elements, number of lines are 1, 2, 3, 4 and 5, which is equals the number of rows of the matrix. So, now we can find out the assignment of this one. If you see I am not just I am writing here, you can assign like this, because you know how to do this thing. One will be this, then you will get C 1 to C 5, C 3 this one will come, C 4 will be 0 and this one C 5 is this. I am not discussing how I am allotting, because already we have discussed this whenever we were doing the assignment problem. So, basically what is the optimal assignment now? C 1 to C 3, then C 2 to C 5, after that C 3 to C 4, then C 4 to C 1 and C 5 to C 2. So, this is the optimal assignment, but if you see basically you are having C 1, C 3, C 4, from C 4 you are coming to C 1 again, but you have not visited all the cities here. So, you have not visited C 2 and C 5. So, by this way whatever optimal assignment is there here, it is not satisfying your criteria of the travelling salesman problem, because it is not visiting all the cities, and from where I am starting I am not coming back to this. Therefore, this travelling salesman problem will not have the optimum solution. So, now what I have to do? We have to first allot what is the lowest element between the unticked elements. Between the unticked elements, if you see the lowest element is 1 over here. So, I am writing I am rewriting this particular table first, it will be clear to you in that case. At first I am writing the, you are having this element C 1, C 2, C 1, C 2, C 3, C 4 and C 5. You are having C 1, C 2, C 3, C 4 and C 5. Values are infinity 2, 0, 13, 27, 0, infinity 4, 5, 0, 0, 4, infinity 0, 4, 0, 1, 19, infinity 2, 0, 0, 6, 7 and infinity. On this, if you see the lowest element between the unticked for the elements which were not covered by the lines, the lowest element is 1. So, what I will do according to the theory, first allot this one, then you start allotting the others. So, that part I can do it obviously like this way, one will be this, on this case it will come to here, for C 3 it will come to here and for C 5 it will come to this. So, once you are allotting these others, for allocation of the others, you follow the normal assignment problem whatever we have done earlier. So, now if you see the allocation C 1 to C 3, C 2 to C 5, then C 3 to C 4, C 4 to C 2 and C 5 to C 1. So, I can make the cycle something like this, C 1 to C 3, C 3 to C 4, C 4 to C 2, C 2 to C 5, C 5 to C 1. So, if you see this now, I have visited all the cities C1, C2, C3, C4, C5 and it is forming one cycle, that is I started from C1 and I am stopping at C1 also. So, this is the optimal path then, and what is the optimal cost? Your optimal cost in that case will be equals to the sum of moving from C1 to C3 on the original table. If you see whatever is the cost we have written, that is 1410 like this, all this from here you can find out the cost and the cost, your cost will become the 48. So, this is one way to do it. You see the next problem. In the next problem, the problem is similar, but I will just do it directly. After doing this, after finding out the row minimum and the column minimum by subtracting, I am writing this one. You are having A, B, C, D and E. You are having 5 cities A, B, C, D and E. The calculation is similar, but I am doing it because of one reason. After subtracting the row minimum column, we will get this table, that is infinity 1 3 0 1, then 1 infinity 2 0 1, 2 1 infinity 2 0 and then 0 0 3 infinity and 4, 0 0 0 3 and infinity. So, if you see after finding the row minimum, that is subtract minimum element from each row, subtract minimum element from each column, we will obtain this table from the given problem. Now, what are the minimum number of lines which will be required to cover all this? If you see, I can draw this, if you wish I can draw this. So, I have covered all the zeros by how many lines? By total 1, 2, 1, 2, 3 and 4, 4 lines. But what is the number of rows? That is number of rows equals to 5. So, therefore, this solution is not optimal solution for the assignment problem. So, since this solution is not the solution of the assignment problem, from the remaining uncovered elements, I have to find out what is the minimum element 1. So, I will subtract it from all other elements, and whenever I am having the intersection, that is this position, I will add the minimum element 1. So, doing that job, I will obtain this table A, B, C, D and E. A, B, C, D and E. The columns will be infinity 0, 2, 0 and 1, then 0 infinity 1, 0, 1, 1, 0 infinity 2 and 0, 0, 0, 3 infinity and 5, 0, 0, 0, 4 and infinity. If you see over here, after subtracting from here using the assignment problem, whatever we do, there are 3 lines I can draw C, D and E, that is something like this. I am just giving one faded on red ink, C, D and E, and on this B and D, that is, if you see I have covered all the zeros. Number of lines are 5, which is equals to number of rows. So, now I can assign. I am leaving it to you basically. If you see, this assignment problem is having the 2 solutions. This assignment problem I can assign in 2 different ways. In both case optimal cost will remain same. The first case you will get A to B, A to B, B to D, C to E, D to A and E to C. You can just do it of your own. If you calculate the cost will become 15. If you see here, this solution assignment problem is not the solution of the TSP, because this is not forming a loop. You are starting from A or any point, but you are not going back to the other one. So, this is your solution 1. The solution 2 you can obtain like this: A to D, B to A, C to E, then D to B, E to C, 1, 2, 3, 4, 5. Here also if you calculate the cost, your cost will become 15 only. But again this solution is also not satisfying the criteria of the TSP. So, this is solution 1, this is solution 2. So, for the solution 2 if you see, now what happens for the solution 2, let me draw first, then I have to now check, since both solution 1 and solution 2 are the solutions of the assignment problem, but not the solution of the TSP. So, now I have to check both the cases separately. I will purposefully I will take the second case first, that will be easier. Let me draw the table first, A, B, C, D, E, this one. If you draw it, and here also I am having A, B, C, D and E. The values are infinite, 0, 2, 0, 1, 0, infinity, 1, 0, 1, 1, 0, infinity, 2, 0, 0, 0, 3, infinity, 5, 0, 0, 0, 4 and infinity. So, if you see from this problem, from here, what is the minimum element after deduction of the rows and elements, or from the uncovered? Minimum elements if you see 1, 1, 1 and 1. How many ones are there? In this, from here it will be clear. Minimum element which is greater than 0, here is 4 ones are there. So, basically I have to check all the 4 cases. All the 4 cases, how you will check? You will check something like this. Case 1. In case 1, what I will do? You assign first A E, assign A E first, that is A to E. That means, you will assign first this A to E, then assign all others. So, if you assign like this, you will obtain the assignment as this: A to E, B to D, you can check it of your own, C to B and D to A and E to C. So, for the case 1, first you assign A to E, then assign the others following the same rule whatever we have done earlier. So, your assignment will be this one. If you see again, this assignment is not satisfying the criteria of the transportation of the travelling salesman problem. So, therefore, this case, this is not the optimal solution. Now, case 2, this one we considered. Now, consider the case 2 over here. In case 2, what you do? You assign the other one, that is say this one. Now, this is not there. So, now you assign say B C, you assign B C, that is you assign first this one, then assign other rows and elements. So, if you do like this, your assignment will be A to D, B to C, C to E, D to B, E to A. Here you see you have covered all the elements, all the cities A to D, then D to B you can write, B to C, C to E and again you are coming back to A, and cost is 16. Therefore, in one case the solution of your travelling salesman problem is follow this path A to D, B, C, E and A, the cost is 6. So, if you see the cost of the optimum TSP is not equals to cost of optimum assignment problem. If you remember, in the earlier case the cost was 15 and here it is 16. So, this is case 2. Now, you consider again the case 3, that is this one you have taken. Now, forget about this, you take case 3. In case 3 what will happen? You assign now the other one, that is assign your B E, that is you assign now this one first. If you assign B E, you will get the optimum assignment as A to D, B to E, C to B, D to A and E to C. Again this path is not cyclic, although it is visiting all the cities, therefore, the solution is not optimum. So, now the other minimum one is there, that is this one. So, your case 4 you have to take now. In case 4 you assign your C A. In assigning C A, what you will obtain? In this case also your if you see the assignment for C A in the same way, that is C to A and all others, you will find that you are not getting the optimum solution. So, for the one solution of AP, you have got 4 different cases, because minimum value 1 was occurring in 4 cases. You are considering case 1, case 2, case 3, case 4 separately. From here only for case 2 I got the optimum solution for the transportation problem. So, this was for the related to case 2. Now, we will see related to case 1 what happens. On the same way, related to case 1 what happens, just once I will draw the table once more, that is you are having A, B, C, D and E. Here also you are having A, B, C, D and E. So, you are writing all the elements infinite 0, 2, 0 and 1, 0, infinite 1, 0 and 1, 1, 0, infinite 2 and 0, 0, 0, 3, infinite 5 and then 0, 0, 0, 4 and infinite. So, in this case again 4 different cases will be occurring, because minimum element is 1 and 1 is occurring in 4 different places. So, just I have done it for the other case. I will just do case 1. In case 1, what you are doing? Assign A E. If you assign A E, that is if you assign this one, in that case your solution will be A to E, then B D, then C to B, D to A and E to C. So, from here if you see A to E, E to you are going to C, C to you are going to B, B to D, D to you are going to again coming back to A. So, therefore, I have visited all the cities and it is cyclic, I am coming back to A only. If you calculate the cost is 16. So, therefore, this is another solution of the travelling salesman problem. So, just like 4 cases I derived for the earlier case, here also I did it for AE, then you will take this one, you have to take, you will take this one, then this one and you may see the solution of this one. One thing may be noted, as I told you from here, that one solution of the TSP I obtained as this path, other solution I am obtaining as this path. So, solution of travelling salesman problem is not unique, that we have to understand, that the solution of travelling salesman problem will not be unique. So, this we did it using the assignment problem or converting the travelling salesman problem as assignment problem, and then you find out the cities or the shortest route where the cost will be minimum. That is other method, as I was telling, there is some approximate method also, which we call approximation algorithm. By this approximation algorithm, you will obtain the shortest path, the cyclic part, but the solution will be approximate, that is the cost or the time may not be optimal. We can obtain the near optimal solution. In the approximate tour TSP tour, we are finding out, or we are selecting a vertex R, which will be a root vertex. As we have told, for the travelling salesman problem, it is not essential that from where I will start and from where I will stop, that is not essential. I can start from anywhere and I can go to anywhere. So, for the travelling salesman problem, at first you are selecting a vertex, then I have to find out a minimum spanning tree. Actually, for shortage of time, I may not be able to complete this minimum spanning tree, but what is minimum spanning tree, at least by one example I will show you. And then this is the step number 2, minimum spanning tree. Then you find out the L is the list of vertices visited in pre-order tree walk of T. What is pre-order tree walk? Then again I will tell, and then we will return the Hamiltonian cycle, that is the cycle which you got. And this is basically your tree for the this is the algorithm for finding out the minimum spanning tree. You just go through, I am not explaining this one. So, what I will do now, I will just let us take this example first. Let us take the example. Suppose you are having, so it is something like this. A, here you are having say CTD, you are having B, you are having F, somewhere here it is C, it is H, it is say somewhere E, and it is G. Some cities are located something like this. Now, we have to find out what would be the shortest route of this one. Let us just find out the minimum spanning tree first for just 1 minute. This is loading. If you see, it is of course not fully, it is, if I just increase it to 16 say, this one is this is the different values whatever we have got for this one, different values we are getting. From A to A it is 0, A to B 2, like this way I am drawing what are the cost matrix, that is for moving from A to B the cost is 2, moving from B to C it is 3, something like this way. So, I am not explaining this one. So, this is the first you will make the cost matrix over here, and once I am making the cost matrix, after that the cost is calculated like this, the Euclidean distance between A and D. If you see, cost of A and E is root over 3 square plus 1 square, that is equals 6.10. Here what I have to do first, I have to find out a key. What is key? If you see, I am making this is little bit larger, so that you can see it. Initially you are having how many nodes? A, B, C, D, E, F, G, H. Initial cost for all of them will be infinity initially. Now, I will start, my root is say A here. Once my root is A, in that case I will make the corresponding key value corresponding to this as 0. From here it is corresponding to this, I will make it as 0, and all others will be infinity. I am making it 0 and all others infinity. If you see here, I have to initialize the values also of pi, and for this the values will be the nil. Initially each and everything will be nil. You have this figure, I am not going to this figure at first. This one I am just writing this. Initially you are having the q is A, B, C, D, E, F, G and H. Now, what is the minimum of this A, B, C, D, E, F, G, H? From the mean value, obviously the value of A is 0, all others are infinity. Your key of A, this is equals to 0, and since q of A is 0, all others are infinity. Now, you remove this A from here, so that your q becomes B, C, D, E, F, G and H. So, your q is this one. Once I got this, what is the adjacent of A now? Adjacent of A will be all this B, C, D, E, F, G and H. So, adjacent of A is B, C, D, E, F and G, H. Now, you calculate the cost between A, B. Cost of A, B, if you see, it is equals to, from the figure, if it is say 2, in that case it is less than the cost of key of B, because initially the B is infinity. So, there will be one value between, there will be a path will come from A to B. So, basically a path will come from A to B like this way. Now, I have to calculate paths from, now I have to calculate after this AC, cost of AC, cost of AD, cost of AE, and then cost of AF and cost of AG and cost of AH. All this I have to calculate just like we have calculated from the given matrix. And from here you can see that once I am calculating all this, you will see that from C to A, from A where I can go. If you see from A, so you are moving like this way, you are calculating the cost, and ultimately you will obtain the minimum spanning tree, something like this. Due to shortage of time, I could not explain the entire thing, but this is the ultimately your, this will be your minimum spanning tree. Why we are saying minimum spanning tree? Because you will find that there will be a minimum spanning tree. What we are telling, you will get a table something like this. You are having here A, B, C, D, E, F, G and H. For A, predecessor is nil, for B it is A, you will find for D it is A, for B it is A, for C it will be B, for D it is A, for E it is D, for F it is E, for G it is E, and for H it is B. So, from here I can obtain the minimum spanning tree. So, once I have obtained the minimum spanning tree, then what I have to do? I have to make a full walk of this. I have to make a full walk of the tree. What do I mean by full walk of the tree? I have to make a full walk of the tree. The full walk of the tree means it will be A, then B, from B it is moving to C, C to you are coming back to B, B to it is H, H to you are coming back to B, B to you are going back to A to you are going to D, D to you are going to E to you are going to say E to you are going to F to you are coming back to E to you are going to G to you are going back to E to you are going back to D to you are going back to A. So, this we are calling as full walk. From this full walk, we are finding out the pre-order tree. What is the pre-order tree now? Your pre-order tree will be from here, you write, you go in this order, whatever has appeared, you write only those only ones, that is A, B, C, B has appeared here. So, you will cut it, after that it is H, B again A has appeared, after that after H D will come, after D this D will not come, then E will come, after E F will come, this after F it will be, this is not coming, G will come, and all this will be cut, and this. So, this is the basically A, B, C, H, D, E, F, G, A, or in other sense if you draw it like this using this pre-order, this one you will obtain, you are having here A, this is your say D, this is the B, this is your F, somewhere here you are having C, here you are having H, you are having E, and you are having F, F is here, somewhere you are having G. So, once I have drawn this, now you follow this path A, B, C, that is A from B, B to C, from C to H, H to D. So, from C to H, from H to you are moving to D, from D to E, from D to E, from E to F, F2 you are moving to G, and from this pre-order G to A. So, this is the optimum path is, therefore, you are getting A to B, B to C, C to H, H to D, D to E, E to F, F to G and G to A. So, this is the approximate tour. If you see, I will tell this is the approximate tour. So, first you are finding out the minimum spanning tree, and after finding out the minimum spanning tree, you have to find out the pre-order tree, and from the pre-order tree you can decide what would be the cycle path. Of course, if you see this one, just A, B, D, F, here you are having say C, somewhere here you are having H, here you are having here you are having H, you are having E, you are having G. If I move something like this, A to B, B to E, E to F, F to G, G to H, H to C, C to B and B to A. That is say A, D, E, G, F, H, C, B and A. If you find out the cost of this one, you will find this is the optimal one. This I have done just by observation, but by our algorithm you will obtain this. So, therefore, we are saying that you will obtain the shortest path which will visit each city only once, and I will come back to the route, that is original city, but the cost will be near optimum, but not optimum. So, please note this thing, that the travelling salesman problem can be solved by the two ways. One is I can form it as an assignment problem and find the solution. Other one is I can form a graph. From the graph I can find out what is the minimum spanning tree. From the minimum spanning tree I can find out what is the pre-order, and from the pre-order I can fix what would be the shortest path, which will be the nearest optimal path. Please note that near optimal, it is not the optimal path. That is the reason we call it as the approximate algorithm. Thank you very much.